Let's talk about something that sounds simple, but can completely break modern systems if misunderstood. In cybersecurity, not all attacks rely on complex exploits or malware. Some are surprisingly simple in concept, overwhelming a system with more data than it can safely process. One such category, often discussed under advanced exploitation techniques, is hydrogen bombing. Welcome to Bluehat Cybersec Academy. This is a term used to describe crashing or degrading servers by sending excessively large requests or payloads. While the name is metaphorical and not a formal industry standard, it captures the idea very well. A single, massively oversized input can behave like a blast wave, exhausting server resources and causing instability, or even downtime. And in this video, we're going to break down exactly what this concept means, how it works at a high level, why it is dangerous, and most importantly, how modern systems defend against it. So let's start from the ground up. Hydrogen bombing refers to a denial of service, or DoS, style technique where an attacker sends extremely large or resource-heavy requests to a server. The goal is to exhaust memory, consume CPU cycles, overload request parsers, saturate network bandwidth, or even crash application services. Instead of sending thousands of small requests as in traditional flooding attacks, this approach may rely on fewer but extremely large payloads that are expensive for the server to process. Think of it like forcing a restaurant kitchen to handle one single order so big and complex that it clogs the entire workflow. Now let's go deeper into how oversized requests actually cause damage. Even well-built systems have limits. Hydrogen bombing exploits those limits by targeting resource allocation during request processing. First, memory exhaustion. When a server accepts a large request body, such as a massive JSON, file upload, or form submission, it may attempt to load it into memory, parse it into structured objects, and validate or sanitize content if the payload is too large. Memory usage spikes. This can lead to application crashes, out-of-memory termination, and severe performance degradation. Next, CPU overload during parsing. Parsing large or deeply nested data structures can be computationally expensive. Attackers may exploit this by forcing repeated decoding operations, complex serialization or deserialization, and inefficient validation loops. Even a single request can monopolize CPU time long enough to delay or block legitimate users. Then we have network and bandwidth saturation. Large payloads consume bandwidth. If multiple such requests are sent, network pipes can become congested. Legitimate traffic is delayed or dropped, and latency increases across services. After that disk, and temporary storage abuse. Some systems temporarily store uploads or request bodies. In those cases, logs may balloon in size, temporary files may fill disk space, and databases or queues may become overwhelmed. And finally, application logic failures. Poorly designed applications often assume inputs are reasonable size. Oversized inputs can break those assumptions, such as maximum array lengths, string size limits, nested object depth, and timeout expectations. Now, while hydrogen bombing is not a formal term used in major standards, similar behavior absolutely exists in real-world attack categories. Now let's talk about real-world analogs, conceptually. For example, large HTTP request body attacks, XML or JSON expansion attacks, including deeply nested structures, file upload abuse, resource exhaustion, DoS techniques. These all fall under a broader umbrella, application layer denial of service attacks, also known as Layer 7 DoS. Now here's why this attack is particularly dangerous. Hydrogen bombing style attacks are concerning because they can be executed with relatively few requests, they may bypass simple rate-limiting systems, they target internal processing costs, not just traffic volume, and they can affect specific endpoints like upload or parsing APIs. And in cloud environments, the impact scales even further. You may see increased infrastructure costs, auto-scaling overload, and even cascading service failures across dependent systems. So how do we defend against something like this? The good news is, modern systems can defend effectively against oversized request abuse when properly designed. First, strict request size limits. One of the most effective defenses is enforcing maximum sizes such as HTTP request body limits, maximum file upload sizes, and maximum header size limits. This ensures no single request can grow beyond a safe threshold. Second, web application firewalls, or WAFs. A WAF can block unusually large payloads, detect abnormal request patterns, and enforce protocol-level constraints, third-rate limiting and throttling. Even if individual requests are large, limiting request frequency helps reduce sustained pressure on the system. Fourth, timeouts and resource caps. Servers should enforce parsing time limits, memory usage caps per request, and CPU execution constraints so a single request cannot monopolize resources indefinitely. Fifth, streaming and chunked processing. Instead of loading entire payloads into memory, systems can process data in streams, handle chunks incrementally, and reject malformed streams early. This significantly reduces peak memory usage. Sixth, input validation at the edge. Validate requests as early as possible, before application logic, at API gateways or reverse proxies, and before deserialization occurs. Early rejection is far cheaper than late processing. And seventh, load balancing and isolation. This includes distributing traffic across multiple nodes, isolating critical services, and using queue-based processing for heavy workloads. Now let's lock in the key takeaway. Hydrogen bombing is best understood as a resource exhaustion attack via oversized inputs. The goal is not complexity, but overwhelming scale. Even a single request, if poorly constrained, can become a denial of service vector. And the core lesson in defending against it is simple but powerful. Never trust input size, structure, or complexity without enforcing strict boundaries. And before we wrap up, let's make this interactive. Here's your challenge for this video. Why do you think a single large request can sometimes be more dangerous than thousands of small ones? What layer of defense do you think is most important? WAF, application limits, or architecture design? And can you think of a real app where oversized input could break functionality instantly? Pause and think about it, because understanding these answers is what separates basic knowledge from real security thinking. And here's one more challenge. Try to identify at least 2 real-world applications you use daily, where request size limits are absolutely critical. And imagine what would happen if those limits didn't exist. And finally, if you found this breakdown useful and want to go deeper into how real-world systems are attacked and defended, make sure to like, share, and subscribe so you don't miss the next breakdown in the series, Advanced Hacking, Attacks, and Exploitation playlist. We'll keep decoding real-world attack techniques, step by step, the way professionals actually understand them. See you in the next one.